Hi. So what I'd like to move on and talk about now is Chapter 3 and the structure of crystalline solids. And what we're going to be discussing in today's lecture are some of the common structures that you see in especially metals and those kind of crystalline solids and how to calculate the various values for those structures. So to first define a little bit, crystalline materials, which is what we're going to be studying in this chapter, they have atoms that pack in periodic three-dimensional arrays. And this is typical of metals and many ceramics and even some polymers. In them you see long-range order across large atomic distances. But for non-crystalline materials, you don't have any kind of periodic packing. And this occurs for some complex structures. It also sometimes occurs in metals if you cool them rapidly, or if, for example, in some metals these days, in more advanced metal structures, they have a whole bunch of alloys that have atoms in them with really different sizes, and then you can get some non-crystalline metals that way. It can also just sort of be a matter of degree. You can have short range order, but not long range order, and those are often called semicrystalline materials. A new vocabulary word for you, we'll use the term amorphous when we're referring to non-crystalline materials. So here's just a few examples that I have to show you for crystalline materials. This is a scanning tunneling microscope image of graphite that we took here at Appalachian State. And you can see here that this is very ordered. So this is obviously a crystalline material with long-range order. If you look at what the structure looks like in sort of a topo plot, then you can see it there. And just borrowing from the web a little bit, this is what the structure of graphite looks like in 3 dimensions. And in STM, obviously, you can only see one plane. You can only see one set of atoms. But what happens is in between planes, they kind of stack like this. So you get a whole bunch of sheets that look like this, and they're stacked one on top of the other. Here's some more images. What you can see in lots of crystalline materials is that you'll have a segment called a domain of the material that has a crystalline structure that looks a certain way. And then right next to that domain will be a domain that's also crystalline, but maybe rotated with respect to its neighbor. And so this is really typical of metals. This is taken from another publication here. This is an example of an amorphous material. This is a scanning electron microscope of polymer spaghetti. So this is obviously amorphous kind of material here. This isn't the atomic scale. This is only magnified 278 times, but you can imagine that it must be amorphous just by the way that it looks. And this is a scanning electron microscope image of an oriented polymer fiber. So here you have short range order, and you can see that the polymer is growing in a specific direction. You can see here it's oriented vertically on your screen, and it's growing that way. And lots of times in polymers, the short range order is going to have a fractal character. And this is an SEM time series lapsed image of something undergoing polymerization. You can see it has kind of a fractal structure as it moves out, so that's fun. Okay, but moving back on, for the energies, what happens is in crystal structures for dense ordered packing, then you're going to have an energy that's going to be minimized. They tend to have lower energies, and they have a typical bond neighbor length that's sitting right down there at the minimum of this bonding energy curve that you can see. So crystalline structures tend to have lower energies than amorphous structures. Now, how do you stack metal atoms to minimize empty space? What we're going to do is we're going to use the hard sphere model, where we assume that the atoms are basically perfect spheres that touch each other. Now, of course, this is a model with many flaws, but it does work pretty well for describing the metal structures that you'll see in the hexagonal closed pack, face-centered cubic, body-centered cubic. It explains those structures very well. And it's a nice model of metallic bonding where you have the atom and then surrounded by that sort of electron sea, if you will. So it works well for that. So what you do is you have these two-dimensional structures with these hard spheres. And then what you do is you form a two-dimensional structure, and then you add another layer on top of that, another layer on top of that. And so we'll describe in some cases how those layers are packed on top of one another. Now, metallic crystal structures, they tend to be densely packed. The reasons for this are typically in the structures that we're going to talk about today, at least, there's only one element present. So we'll talk about the structure for copper, for example, or platinum. So therefore, all the atomic radii are the same. Also, metallic bonding is not directional. Remember that you have that ion core surrounded by the sea of electrons, and the electron sea can go in any direction, which makes the bonding non-directional, unlike covalent bonding. And your nearest neighbor distances tend to be small in order to lower that bond energy in metals. And the electron cloud shields the cores of the ions from each other. And so you have a nice tight short bond. They also have the simplest crystalline structures, so they're the easiest ones to talk about first. The ones that we're going to talk about today are simple cubic, face-centered cubic, hexagonal close-packed, and body-centered cubic structures. And you can see that if you look at atoms that are typically metals here shown in a periodic table, then you can see what structures are used for these metals. Now here they abbreviate hexagonal close packed as CCP, face-centered cubic as CCP instead of FCC, which is what your book does. So you can see that that's in the red. The hexagonal close packed, the HCP, is in the green, body-centered cubic, blue, and so on and so forth. So you can see them all here in this little periodic table. Now it's important to realize, and we'll discuss this in later chapters, that at different temperatures some crystals are going to undergo a phase change. Now unlike a typical phase change where you're going from a solid to a liquid, which is kind of what we discuss in introductory physics courses 1150, 1151, crystalline structures can undergo a phase change from one type of crystalline structure to another type of crystalline structure. For example, iron will go through phase changes and go through from an alpha to a gamma phase, and that changes the structure. So that's kind of interesting. So the first one that we're going to discuss is the simple cubic structure. Sometimes it's abbreviated SC. It's the easiest to talk about because it's the simplest structure, so we always do it first. However, I do want to note this is a pretty rare crystalline structure, and the reason is that it has a very low packing density. So out of all the ones in the periodic table, only polonium has this structure. So the close pack directions are the cube edges, and those are the ones with the highest packing density. Inside the cube, it's kind of not taking up much space with solids there. Let's discuss a little bit of vocabulary. Sometimes you'll talk about the coordination number for a structure, and the coordination number is simply the number of nearest neighbors that each atom has. Okay, so that's the nearest neighbor, so the shortest distance center to center between atoms. So if you look at sort of an extended view of what a simple cubic structure would look like, it's shown here in this little cartoon. And you can see that each corner of the cube is going to touch 6 other neighbors in the shortest possible distance. Okay, so for example, if you look at the one that I'm sort of highlighting and pointing to here, and now extrapolate what that would look like in a larger three-dimensional array, it would touch 6 other neighbors in that way. So the coordination number is 6. Okay. Now here we're going to show the unit cell, and the unit cell is the smallest, simplest structure that shows all the bonds. Okay, so here the unit cell is a little cube, of course, and the atoms are pictured at each one of the cube corners. Another thing that we want to define, and is often talked about for crystalline structures, is the atomic packing factor, and it's abbreviated in your text as APF. The APF, the atomic packing factor, is the volume of the atoms in the unit cell divided by the volume of the unit cell. So basically it's just a fraction that shows how much space is occupied inside the cell. Now APF for a simple cubic structure is 0.52. So let me go through as an example how you would do that calculation. For an atomic packing factor, first you would multiply the number of atoms in that unit cell, and then you would multiply times the volume that each atom has, and then you would divide by the volume of the total cell. Now, oftentimes in your book, they talk about the length of the unit cell. Now, this is a cube, so in each direction along the edge, it's all A. A is the length of the cube here, okay? Now, if you look at what it looks like within the cell, then each corner of that cube is going to slice through one of the atoms, okay? So the cube is made by connecting center to center of all the atoms in the cube. And when you do that, you're going to cut off part of the atoms. Part of the atoms are going to stick out. So at each corner here, see, you have 8 corners to the cube, and at each corner you've got 1/8 of an atom, okay? 1/8 of an atom. So the number of atoms per unit cell is the 8 corners times the 1/8, which gives you, for a simple cubic structure, 1 total atom per unit cell. Now the volume of the cell is the volume of an atom. If you assume a hard sphere model, the volume of a sphere is 4/3 pi r cubed. But the radius of each atom is actually going to be equal to half of the length of the unit cell. You can see here you've got 2 atoms touching at the bottom corners of the cube, and A is equal to 2r there. Okay, so 4/3 pi times the radius cubed would be half of A cubed, and you would put that on top. And now because it is a cube, the volume of the unit cell is just going to be length times width times height. All those are the same. They're equal to A, so it's A cubed. Now, if you multiply all this stuff, divide numerator by denominator, then the A's cancel out, and you end up with 0.52 for the atomic packing factor for a simple cubic structure. Okay, the next one up is the body-centered cubic structure. This is all often abbreviated BCC. The thing is here, the atoms at the corners of the cube are no longer touching each other, unlike in the simple cubic structure. And that's because you've got this atom right here in sort of the middle of the cube. So all the atoms on the corners are touching the one that's on the inside there. Examples of metals that have this structure: chromium, tungsten, alpha phase of iron, tantalum, molybdenum, so on and so forth. The coordination number here, the number of nearest neighbors for each atom, is 8. So you can look at that. The one in the center of the cube is touching all these other atoms on the corners. And of course, there's 8 corners to a cube. So the one in the center is touching 8. Okay, so the coordination number, or the number of nearest neighbors for each atom, is 8. Because of course you can consider any one particular atom to be at the center of another cube. Okay, if that makes sense. Now, this one is going to have 2 atoms per unit cell. All right, you've got the one in the center, of course, and then you add that on to the corners of the cube, okay, which is of course 8 atoms at the corners of the cube, but they're going to be sliced off, so that's times 1/8. So the 2 in the center, the one in the center plus the one atom that comes from all the corners, and that gives you 2 atoms per cell. Okay, the face-centered cubic structure. In this one, what you have is, of course, the atoms at the corners of the cube, but then you have an atom that's sitting at the center of each face of your cube. Now, in this one, there's no atom in the very center, just the ones along the faces. All right? Some examples of this structure: aluminum, copper, gold, lead, nickel, platinum, silver. This one has a much higher coordination number. So to explain this, the coordination number is 12. So if you look at this atom here on the center of this right-hand face, it's touching the 4 at the cube, the corners of this side of the cube. It's also touching each one of these guys that's hitting the face of the front and the back and the top and the bottom faces. It's also touching those. And then of course, if you kind of move it out and imagine that you have an array of these little structures, it would be touching the 4 gray atoms from the neighboring cube, okay? And 4 plus 4 plus 4 is 12, so the coordination number is 12. The FCC structure also has a higher number of atoms per unit cell. Okay, each one of these atoms that sits on the face, all right, is going to get sliced in half. And there's 6 faces. So 6 times a half gives you 3. And then plus the atoms, of course, at the corners times 1/8. So that's 8 corners times 1/8 gives you 1. So that gives you 4 atoms per unit cell. Let's go ahead and calculate the atomic packing factor for an FCC. The atomic packing factor, the APF, is 0.74. I emphasize this because it's the maximum achievable atomic packing factor that you can get. All right, so remembering that you want to multiply for an atomic packing factor the number of atoms per unit cell times the volume of an atom and then divide by the volume of the cell. All right, we already talked about the number of atoms per cell, that's 4, okay? And the volume of your unit cell is A cubed, just like it is because it's still a cubic structure. And then the volume for an atom would be 4/3 pi r cubed. Now, in order to figure out what R is in relationship to A, then we can look kind of along this face right here, okay? So you can see that along this face, you've got one radius from the corner to the atom on the center of the face, and then the atom on the center of the face, you've got 2 radii, right? And then another corner gives you another radius. So that's 4R, 4 radii across the diagonal of that cube. And then the diagonal, of course, of a square, here you have a square where you have a side A and a side A right here. And if you go across the diagonal, that's equal to the square root of 2 times the length of the side. So that's root 2A across that diagonal. So here you have 4R is equal to root 2A, and you can solve for R in terms of A and plug that in. And you would get R is equal to root 2 over 4 times A. So now if I plug that into my formula for the volume of an atom, 4/3 pi r cubed, then I have 4 times 4/3 pi times root 2A over 4 cubed, and then divided by A cubed. And then when you multiply all this stuff out, the A's cancel, and you end up with 0.74 for that ratio for your atomic packing factor. I'd like to add that sometimes, especially if it's been a while since you thought about geometry for this stuff, you should probably pause me and go and stare at it real hard until you make sure that you can understand what I'm saying. That's the beauty, though, of an online lecture. You can always pause the talker. Let's talk about the stacking sequence for an FCC structure. So remember, we talked about adding things in layers. And so if you think of the green layer here as the one on the bottom, we'll call that A. And then the B sites, that's the next layer that you would add on. That's shown here in blue. And what happens is you just put the balls into the minimum point right here in between, forming a little pyramid between the bottom and then the next layer up. And you continue to do that so that all the atoms from B sit in the little low points from the atoms from A. And then you do the exact same thing again for C, okay? For the next layer, you put the orange layer here into the minimum points on B. So what would happen is this is the structure that you would get, for example, if you threw a whole bunch of ping pong balls into a box and gave it a shake until it settled out, all right? And then you have your FCC unit cell. And then what would happen is you would have to turn that on its side in order to see the cartoon that I showed you on the previous page. It's pictured here. And there's your A, B, and C atoms like so. All right. The hexagonal close packed, or HCP structure, is the next one on our list. This one has an AB-AB stacking sequence. All right. The structure of this one is slightly different. Here you see a very hexagonal looking thing. You have a hexagon here, and then you have an atom at the center of the hexagon. All of the atoms nearest neighbor distances are A, as shown here. And then in your next site, you've got atoms sitting in the minimum points in between your hexagon right here, and then you have another structure right here that looks the same as the bottom. So oftentimes they show the HCP structure as sort of an upright solid that's sort of a hexagonal prism that pulls up. And so what they talk about is the C over A ratio. I'll derive it for you in a second, but the C over A ratio would be the height of that prism, C, divided by the nearest neighbor distance between the atoms, which is the length of one side of the hexagon, which is A here. All right. Now, this one has 6 atoms per unit cell. It's probably easiest to really stare at it to see why, okay? You've got your 3 on the inside here, and then you have the ones that get sliced off from the top and the bottom layers, right? And the coordination number is 12, just like in an FCC structure. The atomic packing factor, also like an FCC structure, is the maximum achievable, which is 0.74. All All right, let me do an example problem concerning the HCP crystal structure. So the question for this example problem is, for the HCP crystal structure, show that that ideal C over A ratio is 1.6333. Okay, so note, this is the HCP crystal structure, okay? Here you have your hexagon and then your little triangle in the middle and your hexagon on top. Now, if you think about it, this little B site right here forms a triangular pyramid base, and then the middle atom here on the top is forming the pyramid. So that's the structure I'm going to go back to. This middle atom in green in the top sits in the minimum point of this little triangle right here. So it's kind of, if you want to picture it this way, like forming a little pyramid made out of balls, and you're just looking at the top 4 atoms in that pyramid, okay, symbolized here. So I'm going to do a little bit of geometry to solve all this. Here's my little triangular pyramid that I was talking about, which is the very tip top of the ball pyramid shown on the previous page. At each one of the corners of this little prism here, or pyramid here, I've got an atom. Okay? Now this is an equilateral triangle here on the bottom of the atom, or on the bottom of the pyramid. And then the top atom sits in the minimum of that sort of valley right there, which is going to be at the very dead center of that equilateral triangle. Okay? Now, the nearest neighbor distance between any 2 atoms in an HCP structure is A. Okay? It's also the sides of one of those hexagons. So A here is going to be the distance in between the very top of that pyramid and then along the diagonal of the pyramid to the atom here on this side. Okay, so that's A. Now, if I drop a line, a plumb line basically, from the top of the pyramid to the bottom right there, then that gives me C over 2, okay? That's the height of your hexagonal prism over 2, because of course it has that A stacking, okay? And so you're only going from A to B, you're not going A, B, A, okay? So that's half, so that's C over 2. All right, and now D here would be the distance from this corner of your pyramid right here to the midpoint of the base. Okay, so that's my prism pyramid. Now, if I look at this triangle right here, which is formed from the top of the pyramid to this corner and then along D here to the plumb line C over 2. Okay, so if I look at that triangle, then I can apply the Pythagorean theorem to that triangle. And what I've got is that the square of the sides of this right triangle will then sum to equal the hypotenuse squared. So here I have C over 2 squared plus D squared equals A squared. All right. Now I can also look at this triangle right here. Okay, this is the base of my pyramid. All right. Now this would be one of the legs of that triangle. And of course, if I draw a line halfway along that and then connect it to the midpoint of the triangle, then I can form a little right triangle right here. So each one of the angles in an equilateral triangle is 60 degrees. Half of it would be from the plumb line from here to here. So that's half of that is 30 degrees. So I've got a little right triangle right here with sides A over 2 and then a hypotenuse of D right here. Okay, so I can set up a cosine relationship. The cosine of 30 degrees would be A over 2 over D. And then I can solve for what the cosine is, solve for D, and I get D is equal to A over root 3. Now, from that, I can plug it back into my earlier relationship for my Pythagorean theorem, okay? And then I've gotten rid of one of my variables. So I have C over 2 squared plus D squared, which I'm now subbing in A over root 3 squared is equal to A squared. And now I can solve for C in terms of A. So when I do that, I get C squared is 8/3 A squared. And then solving for C over A, taking the square root of both sides, I get C over A is the root of 8/3, which is 1.633. So that gives us the ratio that it was asked for in the problem. Yet again, probably a good idea. Pause it, stare at it, make sure you get it. We can also compute the theoretical density for any crystalline structure. Now, the thing is, it's a theoretical density because this assumes absolutely no defects. And as we'll see in later chapters, there are lots of defects. So usually your theoretical density will be more dense than your actual density for your material because of the defects in the crystalline solid. So we're going to use rho as the symbol for our density, and rho will be equal to the mass of the atoms in the unit cell divided by the total volume of the unit cell. Okay, so that will give us a unit of kilograms per cubic meter in SI units, or sometimes grams per centimeters cubed, just used because it's convenient. Now, to find this mass of the atoms in the cell, you multiply the number of atoms per cell times the atomic weight of each atom. And then you divide by the volume of the cell, A cubed for A cubed for a cubic cell. And then you multiply that times Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. Okay. Now we've done cubic and hexagonal structures so far, but face-centered, body-centered cubic simple systems don't have to be cubic, okay? They could be other parallel pipette shapes as well. And this often happens, especially if you have, instead of just a single type of atom in your crystalline structure, you have some blend or alloy, then you're going to get more complex looking structures. So here's some of the possibilities. This is a tetragonal structure right here. And in the tetragonal structure, you have a square on the bottom, but then the height of your upright solid isn't the same as the length of the base. All angles here are 90 degrees. You could also have a rhombohedral structure or a trigonal structure. All the lengths are the same, but the angles don't have to be 90 degrees for all of them. You have an orthorhombic structure where none of the lengths of the sides are the same, A, B, C, all different, but they are 90 degrees. You can have a monoclinic structure where A doesn't equal B, doesn't equal C, but not all the angles have to be 90 degrees. Or you can have a triclinic structure where A doesn't equal B, doesn't equal C, and none of the angles are 90 degrees. Okay, so you can have all these different choices of structure. All right, so let's do an example problem. Iodine has an orthorhombic unit cell for which the ABC lattice parameters are 0.479, 0.725, and 0.978 nanometers respectively. If the atomic packing factor and the radius are 0.547 and 0.177 nanometers respectively, then determine the number of atoms in each cell. And the atomic weight of iodine is given as 126.91 grams per mole, so compute its theoretical density. Okay, so first of all, let's compute the volume of the cell. This is an orthorhombic. It looks like this sort of upright solid here. A, B, and C are not the same, but they're all 90-degree angles. So here, you just multiply length times width times height for your cell. So you have 0.479 times 0.725 times 0.978 nanometers for each one of those things. If you write it out so that 0.479 times 10 to the minus 9, then you can get it in terms of meters cubed if you want to, and then you can multiply all three of those things. Then the volume of the cell is 3.4 times 10 to the minus 28 cubic meters. The volume of a single atom, it gave you the radius of the atom as 0.177, so we're going to use 4/3 pi r cubed as the volume of a sphere for the volume of our atom as an approximation to that. And when we do that, we get 2.3 times 10 to the minus 29 cubic meters. So that means that we know our atomic packing factor, it's 0.547, and we can use the formula for the atomic packing factor to calculate the number of atoms, because remember the APF is equal to the number of atoms times the volume of an atom divided by the volume of the cell. So here we have the number times 2.3 times 10 to the minus 29 divided by 3.4 times 10 to the minus 28. We set that equal to 0.547, we solve for our number, and that gives a number approximately equal to 8. Now, we can also use our formula for our theoretical density and solve for it. So now we know the number of atoms in the unit cell. It's 8. We solved for that in part A, so we can plug that in. Here is the atomic weight. It's given in grams per mole, okay? So we're going to multiply times that. And then we divide by the volume of the cell, which we already solved for, 3.4 times 10 to the minus 28. And then we multiply by Avogadro's number. You can see here the purpose of Avogadro's number is as a conversion factor, because if you have your atomic weight in grams per mole, then you need to convert that out. Okay, so that's what we've done here. Multiplying through, doing your dimensional analysis, you can see that you get 4.96 times 10 to the 6 grams per meter cubed. That's not typical for how you give a density. Usually you give it in either kilograms per meter cubed. To convert that, you just divide by 1,000, and you've got it in terms of kilograms per cubic meter. 4.96 times 10 to the 3 kilograms per cubic meter. Another typical unit for density is grams per centimeters cubed. So I've done that conversion here, and you get 4.96 grams per cubic centimeter. All right, so that's our theoretical density. Speaking of density, in general, metals are more dense than ceramics, which are more dense than polymers in general. There is some overlap. Why? Well, metals have close packing, they have metallic bonding, and they have very large atomic masses, right? So if you have a large mass divided by the same volume, you're going to have a higher density. Also, metals undergo that metallic bonding where they have the ionic cores surrounded by the electron C, and that sometimes causes the bonds to be a little shorter. Ceramics, however, are bonded usually in ionic type bonds, and so their bonds are going to be a little larger than the electron C. And they're often made of lighter elements, of course, so that means that the mass that you've got on the top of the numerator is a smaller number, so you have a lower density. Polymers have the lowest packing density. They generally are composed of carbon, which is a very light element, or they have a lot of carbon in them, so that contributes to a low density. But also they're often amorphous, which means they're not going to be as tightly packed, and those interatomic bonds are going to be a little larger. And then composites, of course, are a blend of all the materials, and so they're going to have intermediate values for all of these things because they're going to be, say, for example, a blend of a metal and a polymer or something like that. So you're going to have sort of a range of values, and it depends on what the constituents of your composite are as to what the final value is. Okay, so in the next lecture, we're going to be talking more about crystal systems, about the unit cells. Remember that I defined it for you already. The unit cell is the smallest repetitive volume, which contains the complete lattice pattern of a crystal. And then you set them right next to each other, and you have your crystalline structure. So there's the 7 crystal systems, there's 14 different crystalline lattices, and A, B, and C here are your lattice constants. We're going to be talking more about how the crystal systems work with their notation and how you use them in the next chapter. So let me know if you have any questions, and I hope you enjoyed it.